Our next speaker is one of our first-time attendees, so we're very honored to have him here today. Please join me in welcoming the Senior Vice President and CTO of BlueArc, Shmuel Shottan.
So, am I double mic'd? Yeah. So good afternoon, everybody. Since I'm saying good afternoon, that's a very long title to a short presentation by necessity. I'm between you and lunch, and I dare not present to a hungry mob. So, without further ado, I'm the CTO of BlueArc. I'm here to talk about storage. And paying attention to my esteemed colleagues earlier, two comments. And it's not a long preamble, but two comments. Number one, we're a commercial company, so yes, some of you here might ask me later about more novel ideas, accelerating file system as storage with multiplicity of cores, Sorrento file system for USC, breaking POSIX barriers. We're a commercial company, so long term for me is right now 2 or 3 years. And I'm talking about here and now. Number two, yes, the mission that I have is very simple. For all of you and I think I'm the only one who talks about I/O in this conference, but I'm not sure. For all of you who are accelerating HPC, running the application, throughput and hops per second is where I'm here to minimize. BlueArc was founded in '98, headquartered in San Jose. We are known for high-performance file storage. Yes, we are a network-attached storage company. We are a file system company. We are a product company. You can't sell file systems. We are the number 3 in the top 3 NAS market. I'll talk a little about it, and then I'll peel the onion and talk about what's under the cover. We are proven in HPC environments, and I'll explain what I call the hardware accelerated, tripping on my tongue, architecture. I'm going to go fast by necessity, but our served market today are pretty much in the high performance computing, energy, government, design and simulation labs, etc. Gartner is not exactly the HPC analyst, but that was released actually a week ago, so I grabbed it from the PDF from Gartner, and by vision, I'm proud to be the third one representing BlueArc here. Another slide I'm going to go over fast, just again because I'm between you and lunch. Select research customers. You can read the list yourself, but one comment that helps this list: HPC market, commercial market, genomic research, oil and gas exploration, they do not buy storage. The idea is, am I paying for storage that accelerates my application, because time to market is key? And again, I don't want to leverage on the simulation presentation from Caterpillar, but the proof here is designing storage that allows a simulation I'm leveraging on Caterpillar to complete faster. And I'll talk what are the bottlenecks breaking here. So the essence, it's really large-scale storage, multi-petabytes. I know that it sounds weird after exascale, and exa is now in vogue, but multi-petabyte is really the sweet point today for the HPC performance requirement. An important comment here: you can do a lot of things if you break the standards. As a design goal, we adhere to standard both physical transport layers and protocols, which means CIFS, NFS, fiber channels, SAS, etc. And another comment here, and again paying attention to what I listened earlier, checkpoint and restart is common in HPC. Checkpoint and restart is not going to continue. So the point about features here is a point about having a stable storage, stable file system, checkpoints, etc. So restart is not necessarily there. On a philosophical note here, I am cognizant of the fact that with the best schedulers, with all the applications written, you can't really rely just on the robustness of the file system because you really don't know what's in cache or not. But if you go from 4 hours to the last 3 minutes, the features are important. Another point here, which the best way to describe it is lies, them lies, and benchmarks. And I'm going to talk about benchmarks soon as a proof point. But in reality, I said building storage for your application. So the approach is really a solution-centric. The only thing that is BlueArc here is the foundation and the file system. In reality, you have to have a solution-based approach, which is what we are known for: the network, the WAN, the virtualization, and only then you can measure the application. So what is it all about? It's about building an offload engine for the file system until we'll peel the onion, park it, and think about it very much like the NVIDIA GPU that you saw earlier with x86. And then we'll peel the onion. One of the things that I'd like to talk about, this core NAS engine or file system accelerator, is sustained performance. And again, performance is measured throughput and ops per second. But one thing that the fine-grained parallelism, that I'll talk a little about it, allows is asymptotically, and right now I'll have you accept it at face value. You can catch me later. Asymptotically stay at the performance level, and I'll use the term melt, that doesn't melt and you add load. And as an engineer by trade, still an engineer, always an engineer, I hate graphs where you see the vertical bar saying performance without numbers and a horizontal bar that says load. But really, whether the load is number of client, concurrent clients, etc., and performance is measured by off per second or throughput, whatever, this solution will asymptotically maintain performance. The unique technology vision we are leveraging, and all of it is again a long preamble to talk about parallel file system. The unique technology vision leverage here is an S engine that accelerates file system, complete file system. It's an object-oriented file system in hardware algorithms. I decided not to do a technical dive. FPGA is just a canvas. It's a canvas that was good for us to build it upon to allow this massive parallelism. It's an object-oriented file system. We have partitioning that, again, I'll peel the onion later. Data movement in this core file system engine, data management in multi-core x86 processors. It's an and, it's not an or. The key to selecting the right technology for the task is what can you accelerate? If you look, we spend a lot of time in the engineering department looking at profile of application, doing this 80-20 rule. If you want to move something, and it's difficult, into an algorithm you're implementing in, for the sake of saying it, hardware, note FPGA, so nothing is hard here because you have to have new releases, sometimes bugs that you have to fix, hopefully not frequently. The cost of moving a function to hardware implementation, to state machine-based implementation is large. So really the philosophy is an 80-20 rule. If you do it many times, you'll benefit from acceleration. Both the code that runs on the multi-core x86 on the operating system and the code that runs on the FPGAs are really soft. On a reset, on a boot, both of them are loaded. I struggle with this slide, but I've decided to put it here because the choice was either to show some block diagrams. I don't have nice simulation, but either to show some block diagrams or to get it to a level of really computer architecture 101, and I apologize for the simplicity here. Never mind, somebody gave me a laser pointer, but it's on the upper left is a depiction of a parallel file system. So basically, if I look at it, two buffers, TDP and FDP is from and to engineering terminology. There is a processor. Everything in the file system is an object, and for parallelism, an object can be a file or a directory, and then you have operation parallelize again for a file, for directory, for stable storage, what goes to NVRAM, for directory searches, etc., etc., etc. The little yellow blocks above the purple blocks, wow, that's descriptive, are really what normally is defined as a metadata cache. The parallelism is done by the fact that those structures allow fetching from memory, which is a metadata cache, at various speeds of chunks. Having said all of this, what you get is high degree of parallelism. What you get is pipelining, but I've decided to remove the architecture, but it's really a bidirectional pipeline architecture with high parallelism for the file system. And for offloading, this engine is an offload to the software that's running, so yet another degree of parallelism. So, question that I expected, because you'll be so hungry I won't get questions, but question that I expected was, okay, so why can't you do it with processors? So, being humbled listening to my esteemed colleagues about all the development of hundreds of cores and ideas there, let's just compare it to what's available for a commercial system. Compilers today do not allow to get the parallelism required to get high throughput, high ops per second from multiplicity of processors. Why? Because the applications, NAS is about an application that parks on the same thread, network and storage. So until such compiler technology, which is iffy, is available, a home-brewed architecture was the only way to achieve this performance. I'm going to skip this. I said lies, them, lies, and benchmarks, but I have picked SPECsfs. I have a long-term love-hate relationship with it, but it's the only acceptable benchmark for ops per second in the industry, since it's accepted and the committee is made out of everybody in the industry. I'll use it, and I talked about application versus benchmark. Nice thing about this benchmark is, since it's based on multiplicity of vendors cheating by loading, caching, sure, any other method is really not easy. Long discussion of the core to talk about the one thing that is right now the key to performance of HPC application, which is throughput. So the idea is 20, 30, 40, 100, 200 gigabytes per second to feed this beast, this HPC grid. Remember again, it's an industry of standard and standards win. So any idea to do it without a standard is good for academia until it becomes a standard. Today, the protocols do not allow for aggregating or throughput, and the machines are running NFS. Some of them SIFs, but in this conference, the majority are running pNFS, are running NFS. So the only way is to go to a standard that allows aggregation of throughput through pNFS. So the objectives is really A, scalability. You can start with a metadata server. Actually, the slides are not in the right order. You can start with a metadata server and multiplicity of data movers. The protocols allows scaling, adding increments of the data movers, and scaling the file system capacity and aggregate throughput. I'll explain it a little. What the protocol does, and it's gaining and it's becoming a standard, and I'm looking at others, yeah, but the protocol is gaining. A request is going to a metadata server. The metadata server has the location of the files, and the locations of the files say, go to data mover, you can stripe through across, you can stripe whichever way you want. That's part of how you work with the file system. 5 more minutes. How you work with the file system until pNFS, HPC deployment that needed this aggregation of throughput, assuming that a single Linux system today is 2 gigabytes per second, maybe 3, but 2 gigabytes per second. The file system has stable storage, checkpointing, and synchronous writes. That's about the limit today. InfiniBand or 40 gig Ethernet in both of them. Only way is to aggregate it until about this year. If the need was there to aggregate, proprietary protocols were needed. And proprietary protocols means writing the client software. And if you have to write the client software, that means it's not a standard. You have to update the client software from vendors. We're not the trendsetters. There have been proprietary client software before. We have decided to leverage the standards because they win, and that's the pNFS protocol, which the IETF ratified about a year ago. Development has been done by most vendors over the last 3 or 4 years. Let me combine my high-level short description of what I defined as an accelerated file system with fine-grained parallelism, which for the sake of using the slide that is here, call it FPGA car driver. Bali is a homebrewed name for the OS. And pNFS, this is a case where the performance of the metadata server is key to how many data movers you can add. and how fast can you run it. The ops per second for the metadata server is coming from what I call here the FPGA car driver. The pNFS is the perfect example of leveraging multicore to accelerate the pNFS. Marrying it both together, that's the solution I'll talk about. I picked a couple of points. Yeah, I'm on time. I picked a couple of points that I'd like to talk about. Again, as a commercial vendor, one of the things I want to talk about is multi-protocol access. While pNFS is the protocol for aggregated throughput, you will have other clients, or at least in the environments we sell, there are clients for visualization, etc., old application that have not been rewritten, visualization on SPECsfs, HTTP clients, V3 clients. You want to be able to allow full simultaneous access to those clients, including, again, permission, security, etc. What it saves is the need to migrate data. It doesn't matter how fast you're running on pNFS, if you need to move petabytes so you can visualize over a machine that has SPECsfs, because that's the only protocol that the application understands, you're waiting 10 hours. So the simultaneous access is key. Another feature that I decided to pick, and this is the last one here, is the ability to transparently migrate data. And transparently migrate data translates into the application has no knowledge where the data is, but you moved it to the right tier of storage by value. Can be SSD, can be cheap SATA, can be tape, can be the cloud. And that's done by keeping a stub in the file system, so you gain twice. If you need to do a directory operation, ls, read dir plus, etc., that's done